So you have this equation, and you just basically rearrange and solve for x of the energy balance. When you do that, you get So for the sake of this problem, since you only know CPA, you don't know CPB, you can just assume that this goes to 0. So like delta CP is 0. And then that leaves you with that, and then you know your UA, you know your TA, you know your T, FA naught, CPA, and delta H. So when you plug in everything to here, you can solve for your X from your energy balance. And that gives you a conversion of 0.83. So then you just take this X and you go back here and you can solve for the volume of the reactor. So when you plug everything in, so you know your T naught, T, X. So it comes out to be 1.9 times 10 to the third.
Quick question.
Yeah.
What's the value of your V naught?
What is the value of V naught? Oh, right. Yeah, I forgot that. Good to the calculation. So you can find your V naught from the ideal gas law. So it's equal to your initial flow rate times R T naught over P naught. And yeah, so it gives you the initial flow, initial temperature, and pressure. So that comes out to be 75 liters per second. Yeah, and that's how you know the V naught.
I'm just having, I can't see all that well from here, but for T, are you plugging in the 350 thing?
Yeah, so T is 350 because that's your operating temperature for CSTR.
And the other T naught is 300.
Yeah, the T naught is 300.
So the T is like constant?
Yeah. So with the CSTR, you assume everything's at the exiting temperature and conversion.
Are you able to turn that other light off by chance?
I think so.
Yeah. Okay. Cool. Okay. So that wraps up part A, and then all it changes for part B is the feed pressure is now 10 bar, which is above this vapor pressure component B. Did everyone get this before I erase it? All right.
Is that K correct? Is it supposed to be E to, it just seems too big.
What, this?
Yeah, the K value just seems way too big.
times 10 to the negative 2.
Oh, is that 10 to the 13 or?
This is 10 to the 13.
Yeah.
Yeah, this is for the A. So the prefactor. Yeah, this is the equation it gives you, so, I mean, it's literally given the problem statement, so it doesn't matter. But it is pretty large.
I mean, it's like 10 magnitudes too big for it to make sense.
It's what's given.
Okay.
Yeah.
I don't know. Okay then.
So since the pressure, the feed pressure is now over this vapor pressure of B, you have to think about condensation of species B. So you can write out your stoichiometry table. So I'm gonna go ahead and erase this down. So there's liquid present. The concentration of B in the vapor is going to be, from the ideal gas law, it's going to be equal to just the vapor pressure over RT. When you plug in 350 R and the vapor pressure for B, which is 5 bar, comes out to be 0.17 moles per liter. But you can also count, sorry, you can also calculate the concentration of B with the conversion of 0.83 that you saw for in part A. So, and this is going to be the conversion for part B as well, since the energy balance isn't changing. So you can do that, and that's CB. And then you know your epsilon, your V naught, FA naught, and your temperatures. So from that you can plug in, and the only thing that will change is V naught. You have to use 10 bar instead of 2 bar when you're calculating it, so it comes out to be 15 liters per second now, instead of, I think it was like 75. So when you plug in the conversion of 0.83, 350 over 300, and 15 here, this comes out to be 0.24 moles per liter. And since the concentration of B that is formed from the reaction is greater than the amount that would be present in the vapor from the ideal gas law, you have to consider condensation. So then you can rewrite out your stoichiometry table.
What did you plug in for P, B, 8? You plug in 5 or 10?
So for the this is the vapor pressure of B, so that's 5.